here's what we need to do. We got a reaction here, and this is a redox reaction, and I want to figure out who in this reaction is gaining electrons and who in this reaction is losing electrons. And the way I'm going to be able to do that is by assigning oxidation states for every atom on the reactant side and every atom on the product side. Okay, so here's what we need to do. We need to assign the oxidation. So I like to draw a line right down through the reaction arrow. We need to assign the oxidation state of carbon, of hydrogen, and of oxygen on the reactant side. And then on the product side, we need to assign the oxidation state of carbon, hydrogen, and oxygen. But there's a problem. Time out. Whoa, don't get started. Here's the problem. Oxygen is in more than one thing. And I don't know till I look at it if they're the same or different. So when that happens, when I have the same element in multiple compounds, I call one prime and one double prime. So oxygen prime and oxygen double prime. Now, listen, if they end up having the same oxidation state, you don't need to do that, okay? But you don't know that till you assign it. So I start with a prime and a double prime, okay? Let's go over here to the reactant side. Let's take a look here. We can't do carbon first because it depends on the hydrogen. So we need to do the hydrogen. Hydrogen plus 1. So if the hydrogens are plus 1, that's a total of plus 4. Got to add up to 0. Carbon must be minus 4. And then oxygen is all by itself, pure element, 0. A lot of people say oxygen minus 2, right? But this is elemental oxygen, it's 0. Remember the Brinkelhoffers, right? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Those 7 elements are stable as diatomic molecular elements, okay? And oxygen is one of them, so watch out for that. Okay, so I helped you assign the oxidation states of each atom on the reactant side. I want you to do the same thing on the product side. So I want carbon, hydrogen, oxygen prime, and oxygen double prime. Go ahead. All right, folks, here we go. In order to do this, we must assign the oxidation state of oxygen prime, which is in a covalent compound, and minus 2. That's a total of minus 4. The carbon must be plus 4. Here we have a hydrogen in a covalent compound. That hydrogen is plus 1. And oxygen double prime is in a covalent compound, so that's minus 2. So at the end of the day, folks, oxygen prime and double prime, they ended up being the same. They're both minus 2, so we can get rid of that and just call the oxygen minus 2, since they're both minus 2. But again, you don't know that till you do it. So this is the first step. Any questions on assigning the oxidation states? Okay, here's how we turn this into something meaningful. After assigning the oxidation states for each element on both sides, now we can say, hey, what happened to the elements in this reaction? And if you look, carbon's oxidation state has changed from minus 4 to plus 4. And oxygen's oxidation state has changed from 0 to minus 2. Hydrogen just along for the ride, stayed plus 1 the whole time, right? So what happened here? Well, you need to remember that electrons are negative. And if you remember electrons are negative, it's easy to see who's gaining electrons and who's losing. If carbon goes from a minus 4 to a plus 4, then that means each carbon atom lost 8 electrons. Think about it. If you go from minus 4 on a number line to positive 4, that's a difference of 8. And electrons are negative. You started out negative, now you're positive. You lost 8 electrons. Losing electrons, folks, is oxidation. So that is oxidation. The carbons were oxidized in this reaction. Take a look at what happened to the oxygen. Oxygen goes from 0 to minus 2. Each oxygen has gained 2 electrons. Gaining electrons is reduction. So this is reduction. Try number 6 here. This is a synthesis reaction. So this reaction here, aluminum plus iodine goes to aluminum iodide. You got this, folks. Assign all oxidation states, and then tell me who got oxidized, who got reduced. Okay, guys, hopefully you took a look at this and you said, hey, my reactants are pure elements. Aluminum, pure element, all by itself, 0. Iodine, one of the Brinkelhoffers, right? Elemental form of iodine, the iodines are 0. On this side, we have an ionic compound. Aluminum is a metal, iodine is a nonmetal. So the charges are the oxidation states. So what charge does aluminum have in ionic compound? +3. What charge does iodine have? -1. Okay. And that jives, that's why, if aluminum's +3, that's why you need 3 iodides to cancel it out, make a neutral ionic compound. What happens here? Aluminum goes from 0 to +3. Each aluminum has lost 3 electrons. What happens to the iodine? Iodine goes from 0 to -1. Each iodine has gained 1 electron. Losing electrons is oxidation, and gaining electrons is reduction. So there's your terms: oxidation, loss, reduction, gain. In this synthesis reaction, the metal is being oxidized and the non-metal is being reduced, and that often happens. Okay, fancy word. So oxidation is a fancy word for a process when a metal, okay, essentially loses electrons. Okay, when iron gets oxidized, loses electrons, we call it rusting. Okay, when silver loses electrons, gets oxidized, we say it tarnishes. Okay, copper forms a patina. We have special words for the oxidations of metals. Okay, but the overall term is oxidation, which you probably knew, anyway.